Okay, so we're looking now at section 13.4, and we want to look at more ways to produce alcohols. Let me go down here and make sure I got my pen going. I think I do. This is more ways to produce alcohols. Okay, this time we're going to do it via reduction. Where are we here? Reduction. Okay, so this is Trove says this is a third method to prepare alcohols. What are the first two methods? What are the first two methods? Do you remember that they are? You should answer this before I answer it, okay? I'm going to tell you now, though, because it's a video and you probably had time to think about it. Substitution was the first method we learned in section 13.3. And remember the next one? It was addition. Okay, so here's, and it's going to help you to categorize these in your mind. So a third method to prepare alcohols is by the reduction of a carbonyl. So what's a carbonyl? Well, a carbonyl, you can Google it or you can look it up. Hopefully you have the energy to do that. But I'm going to give you an answer here. Carbonyl. You should draw it out and you should say it. You'll be more comfortable with it if you do. So a third method is to prepare alcohols by reducing carbonyls. Okay, so reduction involves a change in oxidation state. When we did oxidation state in Principles of Chemistry, oxidation state. If you use Trove, Navala Trove's textbook, it's in chapter 3. Oxidation state's a method of electron bookkeeping. This is very important. Very important. I've heard people say before that organic chemistry is all about what the electrons are going to do. What are the electrons going to do? So oxidation is going to help us with that. Now we used electron bookkeeping before in the context of formal charge. And with formal charge, each atom was assigned half the electrons it was sharing, and it was assigned all of the electrons that it wasn't sharing, and that was important too. So what's the formal charge of carbon in methanol? So carbon in methanol looks like this. What's the formal charge of carbon in methanol? And it's 0, right? Because it gets half of the electrons. So the formal charge is equal to the valence number minus half of the shared plus all of the unshared, right? And the valence number of carbon is 4 minus 1/2, and how many are shared here? 8 are shared. And how many are unshared? 0, right? And can you see that that gives you 0? Okay. Formal charge, very important. It turns out oxidation state is going to be useful here too as well. So Klein gives us a couple, a page, a couple slides here on how to calculate oxidation state. There's going to be so few, though, that you're going to eventually memorize it. Okay? So, but let's look at it. Let's look at the way he describes it and see he does a good job with this. So, with formal charge, I sort of drew a picture of this in the previous page. Formal charge, right? That was a bond to a carbon-hydrogen. There's a carbon-hydrogen bond, carbon-oxygen bond, carbon-oxygen bond, right? And carbon, so carbon gets half of the shared, and all of it's unshared, but there were no unshared. And it comes in with 4 electrons because its valence number is 4, right? And so the formal charge of carbon here is 0. But the oxidation state is not 0. And in a moment, I think over right here, I'll remind you how we did oxidation state in Principles of Chemistry. But in organic, we're going to shortcut it a little bit, and we're going to say this. All right, so for oxidation state, we're going to assume that all of the bonds are broken heterolytically. Okay, and that means that all the shared electrons go with one atom or the other, and they're going to go with the atom that's more that has a greater electronegativity. So carbon's more electronegative than hydrogen, and so it gets the electrons for that one, right? It gets the electrons here. These electrons go with the carbon because it's more electronegative than that hydrogen. These ones go with the carbon. These ones go with the carbon, but these ones go with the oxygen because the oxygen's more electronegative than carbon, right? And so if you add up this -3 plus 1, you find that this ends up being -2. The oxidation state of carbon here is -2. All right, so that's it for methanol. Let me remind you how we did this in Principles of Chemistry. So let me switch colors here. Just a minute here. Switch colors for a second. Black. And so for methanol, it is CH4O. That's the molecular formula for this. Okay, let me go back to red now. Okay, so the oxidation state of oxygen is typically -2. The oxidation state of hydrogen is typically +1, right? And so there's only one oxygen in this whole thing, so that's going to be -2. There's 4 hydrogens, so that's going to be +4. And we know that all these together come out to be the charge of the methanol molecule, which is 0, right? So can you see in this case, blank +2 -2, I'm sorry, +4 -2, this is going to be -2, right? So I take that -2 and divide it out over all those carbon atoms. There's only one of them, and so that ends up being the oxidation state of carbon, which is the same thing we got over here, okay? So this is how we did it in Principles of Chemistry. In Organic Chemistry, we're going to shortcut it a little bit because we just don't have that many different kinds of problems to do, so we don't need such an elaborate tool as this. We're going to say, let's divide up all the bonds heterolytically, put the electrons with the atom that is more electronegative, and find out what the charge is, like that. Okay, so it's going to end up being the same thing as we got in the previous course. All right, so the oxidation state, now that's important because we want to talk about oxidizing and reducing carbons. By the way, there's one more rule that I'll remind you about here at the bottom of this slide. But so first of all, look at this. Each of the carbons below have 0 formal charge, right? Because they all have, there's a carbon with 4 bonds and no lone pairs of electrons. And so its formal charge is equal to 0. This formal charge is 0. This carbon here, it has a formal charge of 0. This carbon is a formal charge of, they all do, okay? Calculate the oxidation number for each. So the oxidation number, let me go back to red here. Oxidation number here is +4. So it must be -4, right? The oxidation number, because there's 4 plus 1s, right? It'll be -4. Or another way to do that, like we were doing in the previous slide, is to break all these bonds heterolytically. So all these electrons, they go with the carbon and not with the hydrogen. Here they go with the carbon and not with the hydrogen. Can you see I'm going to have 8 electrons around here when I'm done? Right? I have 8 electrons, but the charge in the core of this carbon is +4. Its valence number is +4. So +4 minus 8 gives -4. Okay? What about this one? Well, that one is going to get, we did this in the previous slide, 6 electrons, and these electrons go off with the oxygen, right? Because that's more electronegative. So this is going to be +4 minus 6, which is going to be -2. Is that right? Yeah, that's right. Yeah, that's right. Okay. -2. Okay, what about this carbon? This carbon, these electrons go off with that guy. These electrons go off here. +4 minus 4 gives 0. Okay, so these electrons go off with that guy. These electrons go off with this guy. So it's only got 2 electrons. So this is going to be +2. Okay, can you guess what this is going to be? This is going to be +4. Okay, so is the conversion of formic acid, which is here, right? Can you see formic acid? Formic acid to carbon dioxide, is that conversion an oxidation or reduction? You should answer that. These videos will be much more useful to you if you try to answer those questions, okay? So you tell me, circle 1, is it oxidation or reduction? It's oxidation, isn't it? Okay. What about formaldehyde to methanol? What I'm going to do is I'm going to draw that to there. That looks like that's a reduction, doesn't it? Can you see that? Okay. So consider pausing the video now and doing Skill Builder 13.3. That's on page, it starts on page 588. Page 588. Okay, before we move off of this slide, I'm going to point one more thing out. It turns out that oxidation, you know what I'm going to do? I'm going to come off of here. Oh, no, I don't want to do that. Oh, wait, we'll come back to this. Keep. Let's go back over to here. I want to get rid of that. Come here. It turns out that, let me make sure I got my right pen here. I don't want black, I want red. Just a minute here. Red. Okay, so it turns out that oxidation more bonds to oxygen or less bonds to hydrogen. Okay, and I don't want that. Just a minute here. I don't want that. Sorry. I need some new technology. It's a new version of reduction. Can you see where I'm going with this? Is less bonds to oxygen or more bonds to hydrogen. Okay, just a minute here. My wife is calling. Might be one of my children. Just a moment, please. Hello? Yeah. I want you to use it sparingly, but I don't remember if I gave a hard rule on that. Listen, I'm doing a video right now. Yep, love you. Bye-bye. Okay, one of my children, so pardon me. All right, so oxidation is more bonds to oxygen. Look at that. And reduction is less bonds to oxygen. Okay. Anyways, that's something that will that may help you sort of in the future. Let's go back to this presentation here, and say Shift F5. Okay. So let's move on. Now, don't forget what we're doing here is we're sort of setting the scene. Where am I here? Setting the scene so we can learn more reactions to alcohols, more reactions to make alcohols, okay? So we said the reduction of a carbonyl is another way to do it. So can you see that I'm having here, I have, how many bonds to oxygen do I have here? 2 bonds to, oops, just a second here. 2 oxygen. How many bonds to hydrogen here? 0 bonds to hydrogen here, right? How many bonds to oxygen do I have here? 1 bond to oxygen. And how many bonds to hydrogens? There's a hydrogen here, isn't there? So 1 bond to hydrogen, okay? So the oxidation state of carbon here was 0. The oxidation state of carbon, sorry my handwriting, okay? The oxidation state over here was, just a minute here, remember we did it like this, we went like that. So 2, wait a second. That's if these are hydrogens, it's 0. Let's suppose these are hydrogens also, okay? And so I guess in that case I had 2 here. In this case I have 3. So 2, 6, this would be plus, rather minus 2, right? Minus 2 over here. It's 0 over here, and minus 2 over here. So indeed, it's a reduction. Agreed? 0 to minus 2. That's a reduction. All right. So, but it requires a reducing agent, and that's where we enter. That's where we're going with this conversation. Is a reducing agent oxidized or reduced? That is not a super important question here. Where's my pen? I've lost my pen. There we go. Not a super important question here. I'm going to put a line through it. Probably should have got rid of that question over there. If you were to design a reducing agent, what elements would be necessary? It would be something with some extra electrons, that's for sure. And then another question, which I'm going to say is not super important, but a good thing for you to think about. This will help you later. Would an acid such as hydrochloric acid be an appropriate reducing agent or not? So what I said, if you were requiring a reducing agent, what elements would be necessary? Something with extra... Man, my handwriting is terrible today, isn't it? Let me start over again. Electrons. Would an acid such as HCl be an appropriate reducing agent? Why or why not? No, it would not be, right? Because HCl has a tendency to do that, right? And chloride, very happy all on its own. It's not going to do anything. Not reactive, unreactive. And this guy has no extra electrons, right? So no. HCl would not be. Okay, still building the story here for the reactions that we're trying to memorize from section 13.4. Okay, so 3 reducing agents you should know. So here's one. Here's one reducing agent, is H2. And this is typically done in the presence of platinum, palladium, or nickel. All right? And can you see I've got a reduction going on here from here to here? That's a reduction, right? Because I've got fewer bonds to oxygen. When I'm saying fewer bonds, I'm talking about from the carbon. You know, I wonder if that's obvious to you. Was that obvious to you guys? Let me write this out in case it's not. Let me go here, boom. From carbon to oxygen. I'm not sure that that was obvious to you. Okay, it's fewer bonds from the carbon to the oxygen, right? Can you see that there's 2 here? And there's only 1 here. Okay, so this is a reduction. Okay, and here's our first reducing agents, H2. This is typically done in extreme conditions such as high temperature and or pressure. So H2 is the first reagent that we've got to do that. Okay, the next one is sodium borohydride. Sodium borohydride, NaBH4, sodium borohydride. And this is done either in ethanol, methanol, or I forget what the name of that stuff is. Ethanol, methanol, or that other stuff. Okay, let's go back here. Wait a second. This was 95%. That's good yield. Okay, 90% is considered good yield. Okay, so sodium borohydride. Here's the mechanism for how this works. Sodium borohydride acts as a deliverer of hydride, H minus. This is how it acts. Okay, so you get your BH3 here, and your H, your hydride is riding on piggyback on top of this BH3. Okay, can you see? Excuse me. Can you see that? So what happens is I'm going to go maybe with a different color here, so that I'm just going to really just repeating what Tro is, or not Tro, but what Klein is saying here. Let me go with blue. So I'm just going to repeat what he says, right? He says, all right, the electrons come here, and bam, they hit that. And when they do, these electrons come off and go on that oxygen. And these electrons right here are these electrons here. You see it? And these electrons are these electrons, right? Okay, so this is the product of that reaction. The hydride comes on here, and it makes an alkoxide. right? Can you see that you've got like a deprotonated alcohol here? Okay, and now all we need to do is just give this alkoxide, just surround it with water molecules, and it will take one of the hydrogen atoms, right? You see that? And it's going to leave a hydroxide in its wake. And so now we have a secondary alcohol. Aha. And we've done it. We've made an alcohol, okay? So let me go back to the previous slide. Do you see how we made an alcohol? That was our first method. I said we're going to have 3 reducing agents. There's our alcohol. 3 reducing agents. The first one is hydride. The second one is sodium borohydride. Okay? And the third one is lithium aluminum hydride. Okay? Which we'll oftentimes write as LaH. See it here? Okay. So LaH, which is really lithium, here's my aluminum hydride. Where's the lithium? It's a counterion, that's all. That's all it is, just a counterion. So it's really the aluminum hydride that's the sort of actor, and it acts as a delivery agent for the hydride. So look at this. Here's my hydride. H minus is called hydride. These electrons come here. Oops. Whoa. These electrons come here. Boom. And hit that carbon. And these electrons come here. Boom. And make another alkoxide, right? There's my alkoxide again. Alkoxide then is in a bath of water. That's our second step, right? We add water to it, and when we add water to it, the alkoxide, because there's a billion of these water molecules for every one of these alkoxides, the alkoxide, boom, takes the water molecule, and there we go. There's our secondary alcohol. Secondary alcohol. Now, there's one thing I want to point out, which Klein doesn't say anything about here, but you should be thinking about this. And that is this going to be in the R configuration or the S configuration? Ooh, you know what? I'm not even going to answer that right now. I want you to think about that. In order to answer that, you've got to chew on the mechanism, okay? So is this going to be in the R configuration or the S configuration? And you need the mechanism for that. You know what I'm going to do? I'm going to try to remember to ask this on a quiz, okay? What am I doing here? My pen is not working nicely. Nope. Okay. All right. So is it going to be in the R configuration or the S configuration? You need the mechanism for that. So think about that. I'm not going to answer that here on the slide, but hopefully I will remember to ask that in a quiz. All right, so note that this is it's not something you would know from looking at the mechanisms, but Klein tells us that lithium aluminum hydride is significantly more reactive than sodium borohydride. This, by the way, let me give you the other lithium aluminum hydride. Okay, it's the same thing here. I show you both because you need to. Because depending on the source of the question that's written for you for your quiz or exam, whether I write it or I get it from Klein, I think I'm probably going to write it. I'm sorry, my pad is so... okay. I'm probably going to write it as LiAlH4, lithium aluminum hydride, and Klein writes it like LaH. They're the same thing. So you need to be comfortable with both. So LaH is significantly more reactive than sodium borohydride. Thus, LaH reacts violently with water. Why would that be the case? Why would that react violently with water? Why would that react violently with water? Come to class ready to answer that. Why would it react violently with water? It'll help you if you get it, okay? It's not a side note. Now, you can't just memorize that, but it's going to help you if you get it, all right? So, if that's the case, then lithium aluminum hydride has to be kept separate from the water. 2 steps, you see that? But sodium borohydride can be right in the same bucket as the water. Okay, why? Because lithium aluminum hydride is more reactive, and it's going to react with the water if you put it at the same time. So first of all, we treat this stuff with lithium aluminum hydride, then we put the water in. All right? And your question is, the question for you is, why? Why would it react violently with water if it's so reactive? Okay? All right, so in review now. In review, we have 3 new ways to make alcohols. They are, this was the first one we did, number 1. This was the second one we did, number 2. And this one's just shown here in methanol. It could be or ethanol, or what's the third one we did? Okay, the third solvent. What's the third solvent we did for that, right? Okay, and then the third reducing agent was lithium aluminum hydride. And the only solvent that we used in this text was water. I'm sorry, no, this was not the solvent. This would have to be done in a polar aprotic solvent. Polar aprotic solvent. If there's not an aprotic solvent that comes immediately to mind, look that up right now. Yes, look it up. Look it up. It'll help you memorize it if you do. And this has to be done in a polar aprotic solvent. Why? And then after it's reacted with the carbonyl, then we chase it with water to give it a proton so that we make our alcohol. Okay? Work through those mechanisms and you will see why. It's really going to help you settle in your head if you do that. Okay, now let's nuance this a little bit. All right, so it turns out that lithium aluminum hydride is strong enough to produce esters and carboxylic acids also. All right, so you see, here's your carbonyl carbon. I switched to blue. Did you notice that? Here's my carbonyl carbon. Here's a carboxylic acid, and here's an ester. Aha! Lithium aluminum hydride is strong enough to react with that also, right? But this is not. Sodium borohydride is not. So sodium borohydride won't touch that, and sodium borohydride won't touch that, but lithium aluminum hydride will. Let's look at the mechanism. So first of all, the hydride comes and hits that carbonyl carbon, right? And that comes off and makes an alkoxide. It's kind of like an alkoxide actually, right? But you still have this guy over here. Well, wait a second. Now this is a leaving group. So you see if this guy comes, if this guy comes back down, this guy can leave. You see that? Now, pause the video and draw the product of that reaction right there. Draw the reaction of this mechanism. Okay, let me suppose you did. And I'm going to draw it. Right? Can you see that? My RCH. Here's my C. That's RCH. Okay? And then these electrons coming back down, making a double bond, and there they are. Okay, and there's still 2 lone pairs of electrons here. Okay, so this picture takes us to the next slide, and here, that's what we have right here. Now, with the second round, we have another hydride that comes and hits this guy, and this is what we had last time. This is what you saw before. And that goes up here, makes our alkoxide, right? And then we add water to it. And after we add water to it, there we go. There's our alcohol, okay? And here we have, watch this, a primary alcohol. Okay, so here's a good question for you. Which steps are reversible? I'm not going to go over that with you right now. But let me point something out here. If you, I don't think there's any way to learn this without drawing the mechanisms out multiple times in your head. Or I'm sorry, whoa, not in your head. On a piece of paper. I don't think there's any way to do that, and you need to go through here and look at these, write them out. You need to write them out and follow the electrons. Okay, now that we've got that, we see, let me go back here, we've got a primary alcohol here at the end, and there's one more wait a second, 36, I gotcha, okay, and this is it. So this is, I want you to do, predict the products for the following processes. And I want you to pause the video, and it's going to be a long video, I know. Pause the video and work these out. And when you're done, I'm going to work them out and the remainder of this video. Did you pause the video? If you didn't, pause it now. Pause. Do. Okay, now, let's suppose you paused it. I'm going to come over here, and I'm going to come here, and I'm going to go here. Okay, this is the problem that you had before. I'm going to work it out. Okay, so the first one, let me get a little thicker here. Okay, so the first one I'm going to do is here. I'm not going to do the mechanism. I'm just going to do it. This is in water. Okay, and what we know is that sodium borohydride will not react with a double bond. It will not react with an ester. Uh-oh, my pen's giving me trouble. But it will react with this guy here, right? So if that's the case, I'm going to draw this out. That's what, a 7-membered ring? And a double bond here. I'm going to count these up just in case. 1, 2, 3, 4. Oxygen is my 5, 6, and 7. Watch this. 1, 2, 3, 4, 5, 6, and 7. A, B, C. A, B, C. Okay, yep. And this carbonyl carbon, that's going to get reduced to an alcohol, right? Because sodium borohydride is not reactive enough to work with an ester, and it's not reactive enough to work with a double bond or an alkene, but it is reactive enough to work with a carbonyl, okay? With a simple carbonyl, and that is an aldehyde or ketone. Now let's change colors here, and we'll go with lithium aluminum hydride and then chase it with water. Don't forget, this is 2 separate steps here. This is not. Okay, now I'm going to come over here and in red. Can you just see past the black? Okay, the red's not going to touch the double bond, but it is going to reduce that. I am really sorry. My pen is struggling. Just a minute here. Just a minute here. Sorry. It is going to reduce that. And it's going to reduce this. Okay, now this is complicated. I'm going to go with, Okay. Can you just see past the black? I don't want to erase all that. Okay, watch this. 1, 2, 3, 4, 5, 6, 7, 8. Okay? And off the 4 comes an A and a B. So watch this. 1, 2, 3, 4, 5. And it looks like there's a cis bond here, right? You see that? Or a Z bond there between 5 and 6. 1, 2, 3, 4, 5. And between 5 and 6, okay, and it's a cis bond, so that's going to have to go this way, right, to 7. And it looks like 8 goes that way, and 8's an oxygen. There's my 7, and 8 is an oxygen. Okay. Now, off of 4 comes A and B, and those are both carbons. A, B. Okay, and another oxygen comes off of there. Okay, so that's going to end up being a hydrogen. This is going to end up being a hydrogen, right? Because I had excess water. Wow. Okay, and this is going to end up being an oxygen, an alcohol, right? Okay, so this is the answer for lithium aluminum hydride, and oops, that was supposed to be H2O. Okay. The mechanism is probably going to help you figure that out. I have a feeling someone's going to want to see that worked out. Really, you should try. Ask me how to do that in class, but you need to try that first. I'm going to ask you to see your notes. When you ask me, I'm going to say, let me see your notes on that. What did you do with the mechanism? And I'll give you a hint. The mechanism is going to be here, right? Just a minute here. Well, no, this isn't the mechanism. This is a reaction, okay? But watch this. And you can see, if you just take that, that's an example of it. This is we did cyclic. This is not cyclic. There's my answer, okay? But here's the reason why. So go to slide 35 and follow it through. 35 and 36. 35 and 36, and you'll get this answer here. Okay? Super valuable. Complicated, but not nearly as bad as it looks. Okay, hope that's helpful.